Today, I'd like to talk about my new result, which are related to historic behavior and Dirac physical measure of diffeomorphism having nowadays very popular concept provided by Lorenzo, of course, with Christian Bonacci, called a blender, and the C1 robust homoclinic tangency. Every content I talk today is contained in the preprint written with Yushi Nakano and Teruhiko Soma, which was uploaded to the archive 1 or 2 months ago. Okay, next one. So let's get started. This is the content of today's talk. It is simple story, so it may be over sooner than I have time for. So first, let us start to recall several key definitions of this study. Rare and Tarkin said that a map of F defined on M has historic behavior if it satisfies following condition. There is a point of X in M such that the average of the some Dirac measure supported on the forward orbit of X does not converge to anything if n goes to infinity in weak star topology. For this concept, Tarkins presented the following open question. Are there persistent classes of smooth dynamical systems that the set of initial states which give rise to the orbit with historic behavior has a positive back measure? This open question has already been answered positively by Soma and myself. This answer is generalization of Corey and Vargas model to two-dimensional diffeomorphism with homoclinic tangency. In fact, we show that any C2 Newhouse open set of two-dimensional diffeomorphism has a dense subset, any diffeomorphism in which has a historic wandering domain. Here, the wandering domain is open, and hence it has positive back measure. Hence, it is a positive answer to the Tarkin's last problem. Note that this discussion can be applied to the class at least C2, but not to C1 and also C infinity or C omega classes. Recently, for C infinity or C omega classes, I heard Belgi and Bieber gave another positive answer to the Tarkin's last problem by different approach from ours. But both discussions cannot be applied to the C1 diffeomorphism. So we can ask whether or not Tarkin's last problem can be answered positively in the C1 category. This is one of motivation of our study. In addition to the historicity of the wandering domain, we also have observed another property called Dirac physical measure. The idea of Dirac physical measure is opposite idea to the idea of historic behavior. And its idea more traditional and popular than that of historicity. Definition, we say that a map of F defined on M has non-trivial physical measure mu associated with non-empty open set D in M if it satisfies that for any point of X in D, the average of some Dirac measure supported on the forward orbit of X converges to the nu as n goes to infinity. And moreover, the support of the nu is equal to the saddle periodic point. orbit. Note that Dirac physical measure supported on the attracting set, for example, think is trivial. But on the other hand, it is not trivial if it's supported on the non-attracting invariant set, for example, a saddle periodic point. This concept was already studied by Sanhin, Sun, and Vargas 2010, and also Sanhin and Vargas 2011 in some two-dimensional flow, Shelly flow. So I think it is interesting if we find the different phases have a non-trivial Dirac physical measure associated with some wandering domain. So I've been using the word of the wandering domain with a definition. So let's give a proper definition of this keyword. Definition: a non-empty connected open set D in M is non-trivial wandering domain for F if it satisfies the following condition. One, every word image of the D here has no intersection each other. Moreover, union of the omega limit set starting from D is not equal to a single periodic orbit. This definition can be found in the book Dumero, Sebastian Feinstein, 1989. The first condition is associated with a wandering situation. And the second one is associated with its non-triviality. So using this definition, we are now ready to state our main result. Theorem A, there is three-dimensional diffeomorphism F in the C1 Newhouse domain, where the C1 Newhouse domain, also known as a Bonacci-Gias domain in Japan, means an open set of diffeomorphism having C1 robust homoclinic tangency. Such an open set presented by Bonacci and Gias for any dimension, at least three. Anyway, we have a three-dimensional diffeomorphism F such that for every CR neighborhood of F where R is any integer, at least one, but not infinity, contain two sets H and P of diffeomorphism with the following condition. One, every diffeomorphism belonging to the set of H has historic contracting wandering domain. And also, every diffeomorphism belonging to the other set of P has non-trivial Dirac physical measure associated with contracting wandering domain. This is the first result of our preprint, but since it is consequence asserting the existence of a single diffeomorphism, so it is too natural to ask its generality, that is how abundant, how much, how many diffeomorphism with same property as F of theorem A. To this question, we can extend it to small arc, a one parameter family of the diffeomorphism in the next result, theorem B. We show that.
What's the properties of the set H and P?
H diffeomorphism belonging to H has a contracting.
Yeah, but are they dense or?
What? So sorry.
Are H and P dense?
No. I say just. Yeah, I say just the existence. Yeah. Okay. This theorem said there exists one diffeomorphism, one example. Okay. In a C1 diffeomorphism, which an arbitrary close to approximated by a different element of H or P.
Okay, so it's dense in the neighborhood.
Yes.
Or
Yes.
they accumulate,
There
actually.
is one point that accumulates on the guide. Okay, thanks.
Yes, yes. Okay. 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 So then you ask, okay, how abundant, how many are different prisms with the same property as F with theorem A? So to this question, I gave this result. There is a one parameter family, of course. F0 is equal to F of theorem A, and the one parameter family F mu is contained in the intersection between the closure of H and that of the P given in the theorem A. I think the existence of the set of H is one of supporting evidence of the affirmative answer to the Tarkin's loss problem in the C1 topology. But perhaps you might ask, whether or not there exists more such a different prism having some same property. For example, robustness of this property, that is the existence of one parameter family, existence open set of different prism with such a property. But I think it is difficult problem. In fact, in the C2 topology, in the C2 Newhouse domain, no such a presence has yet been confirmed. But I think there exists a dense subset of any or some, I'm not sure if it's any or some C1 Newhouse set domain for every different prism has historic behavior. In fact, compared with the result given in the paper, Soma and myself, we show that any C2 Newhouse domain for the two-dimensional different prism contain a dense subset where every element, every different prism has historic behavior. Then the similar result might be true in the C1 domain. This may be contained in the collaboration I have just started last week with Lorenzo. Anyway, robustness of the positive or negative solution of the Tarkin's last problem is still open in every regularity, even in the C1 or C2 topology. Honestly speaking, I was give up trying to prove it. So I hope anyone will solve it or give some different view about the Tarkin's last problem in the future. In the end of the
sorry, I have a comment. In all your discussion, there is the case of T1 to diffuse in dimension 2 that you don't consider at all. This is because the Gugu's result about that in the C1 topology and in dimension 2 there are not robust tangencies, or is related to that?
Yes,
you don't have Newhouse domains, indeed.
Yes, yes. Yeah, I C1 topology.
Yes, I think that in full surface diffeomorphism in the C1 topology, you have no Newhouse domains, and that is more or less why you cannot start a discussion, I suppose.
Yes, yes. We talked last week, I think. But in my paper with Soma, we just show about the C2 different.
Oh, okay. I just saw a comment.
Okay, thank you very much. And then maybe this is this study is the first step about the C1 Newhouse domain, I think. Okay, I continue. It's okay.
Question, please.
Question?
Yes.
Please.
If you start with some domain with universal dynamics, maybe we could get density.
In C1 topology?
I think so. In C1 topology, certainly we have, but I think there are there was works on C infinite universal dynamics by Toureff on, if I'm not wrong.
I'm not. I'm familiar with
That is,
universal.
if any phenomena appear everywhere in these open sets, then if you get one, maybe you can get densely.
Really? Okay. I will study about your paper about university. But
No, it's not our paper, because our paper is on the C1 topology. You don't want C1 topology, but maybe it was just that comment. Sorry.
Okay, thank you very much. Okay, and in the end of the introduction, I'd like to mention a few comments about more than 3 dimensions. Our results are just given in the 3 dimension because it is essential, but it can be extended to high dimension at least 3 if you suppose analogous condition. For example, the codimension of the tangency is equal to 1, or the center direction of the blender is always equal to the dimension 1. But I think the tangency with a high dimension, a high codimension, the technique of Pavlov variantus and Artem Liebeck's might work in any case of the high codimension tangency. So it might be one of future works we should do if possible. Okay.
I have another comment also. Maybe
okay.
it's a good idea to compare your result with my recent result about also historic contracting wandering domains in C1 new house domains. I think that is useful to do this.
Okay, thank you very much. Let's consider it together, if possible. Okay?
Yes.
Okay, let's continue the. Okay, now I will show you how to construct a different prism F of theorem A. It is constructed using blender-horseshoe with homoclinic tangency. First, we consider 4 real positive constants, lambda SS and lambda CS0 and lambda CS1, lambda U. The first one, lambda SS, and the last one, lambda U, are corresponding to the strong, stable, and unstable eigenvalue for the blender we want. On the other hand, the pair of middle constant is corresponding to the center stable eigenvalue. We will suppose that the one of center stable eigenvalue, lambda CS0, is smaller than 1/2, and the other one, lambda CS1, is bigger than 1/2. Moreover, we have to suppose that the sum of these center stable eigenvalue is bigger than 1. This means that the distance from the lambda CS0 to 1 is smaller than the distance from the 0 to lambda CS0. This condition will guarantee the superposition region for the blender we want. Moreover, to obtain the wandering domain later, we have to suppose that center and unstable eigenvalues satisfy such a partially dissipative condition. It means that the product of center stable eigenvalue is relatively small compared to the unstable eigenvalue lambda U. Using them, we consider CS blender horseshoe in R3 as follows. Let B be the unit cube in R3, and V0 and V1 are parallel subcube defined by using the lambda U inverse as shown in the picture. And if we consider the linear map and affine map on these subcube respectively like this, we have just we have image of these subcubes in B as in the picture. As you may notice that this blender is somewhat different from the ordinary blender presented by Lorenzo. In fact, it is imbalanced between top and bottom and left and right, because we suppose the partially dissipative condition for the center stable direction. Let's see this asymmetric structure in detail. If you observe it from the standpoint above XY plane, the image projected on XY plane is just an image given by affine horseshoe map. On the other hand, if we observe it along the Z direction, the dynamics are controlled such an iterated function system. One is strongly contracted by lambda CSL, while the other is weakly contracted by lambda CS1 from the contraction associated with the center eigenvalues. It assures that the image of this function are overlapped. That is, it gives a superposition region or distinguished property for the blender We now have obtained an example of CS blender horseshoe, but which is asymmetric and to satisfy partially dissipative condition. Note that such asymmetric condition cannot be fulfilled if the slope of the center direction are close to the identity. Therefore, such a symmetric blender horseshoe might be C1 away from the usual blender, which can be derived from the heterodimension cycle via strongly homoclinic intersection of the saddle node by an arbitrary small perturbation provided by paper Bonacci and GS 208. This means that what I am describing now is not immediately applicable to the content of any heterodimensional cycle study by Bonacci and GS 208. Can you detect such a asymmetric blender from any heterodimensional cycle? This problem may be in relation with the ongoing project with Lorenzo, as mentioned before. Okay. Next, besides the blender, we need a homoclinic tangency to detect or construct a wandering domain. So let us observe what type of homoclinic tangency should be supposed to the blender. It has a shallow fixed point at the origin of U index denoted by P. From the definition of affine form, the segment from the 0 to 1 in the x-axis belong to the local unstable manifold. Also, from the definition, the local unstable manifold can be automatically extended upward like this. In the next step, we consider two types of homoclinic tangency associated with unstable manifold and local stable manifold of P. In the first case, not good one, the tangent space at the homoclinic tangency at X is parallel to the y-axis by vertical direction, which is local strong manifold of P. If you see it from the above of XY plane, it is exactly same as a two-dimensional model of Korean vargas. Hence, you might obtain similar result providing by Korean vargas with help of several techniques in a high dimension, for example, paper of Paris and Vienna, 1984. However, such a strategy will not get us out of the Shitsu category. And moreover, furthermore, by a little perturbation, it is possible to maintain this tangency, but make a direction different from the vertical direction. Thus, the tangent direction at forward image, such a pattern of tangency are gradually close to the center stable direction, since it is placed strongly along the vertical direction. The Corey-and-Barks argument no longer seems to work in this situation. That is, it is not a good idea to assume such a setting as a starting point of our study. So let us try to different setting like this. The tangent space at the homoclinic tangency at x is now parallel to the x-axis, center stable direction of P. Different from the first setting, even if you add a small perturbation to this type of tangency, the tangent direction at forward image always stayed close to the center stable direction. This implies that the second type of tangency is more general than that of the first one. Of course, we cannot apply Corey-Barks argument to such a situation, but we can use several results about C1 robust tangency presented by Lorenzo and Bonacci. Okay. Now let us describe this type of tangency by using Laguerre form. Let U be a small delta neighborhood of plane x equal to the 1/2 the yellow part in this cube for any point xyz in this cube yellow part. We assume that two composition of f satisfy following formula. Okay. Following formula. Okay. The first coordinate quadratic with respect to x, and it contains first order term of z, and the second coordinate depends on y, and the third one only depends on x, like a three-dimensional map. By this two composition of f, the small segment in a local unstable manifold contained in the point 1/2 there is transformed to the quadratic curve here, which is tangent to the local stable manifold of P. The tangent space at the tangency is parallel to the CS direction. So let us write a summary of the definition F of now. The map of F restricted on the subcube V0 and V1 was just an affine blender horseshoe defined like this. By the partial dissipative condition, this map has such an asymmetric structure. Moreover, F2 restricted on yellow cube is defined such a quadratic forms. So we call the non-hyperbolic invariant set for such an F the wide blender horseshoe. That is, the wide blender horseshoe means invariant set, which is consisted of blender horseshoe. Of course, it is uniformly hyperbolic set, and also has the orbit of homoclinic tangency. From this setting, we immediately obtain C1 robust homoclinic tangency. In fact, if we consider the small section sigma, which is parallel to the local stable manifold of the blender, and its inverse image become such a figure, so-called holding manifold. Note that it has non-transverse intersection with unstable manifold of the blender because of blender distinguished property. Thus, from the paper of Bonacci and Gias 2012, we have the following result. Let there be a different phase satisfied formula above. Then the F has a C1 robust homoclinic tangency associated with CS blender horseshoe. Okay. In order to show our main theorem A, it is enough to provide the following key result, say theorem A prime. Every CR neighborhood of the F defined above, where the R is any positive integer, at least one, contain different phase, which is historic contracting wandering domain. Moreover, it contains another different phase having a non-trivial Dirac physical measure associated with contracting wandering domain. Using this result and the previous proposition about the C1 robust tangency, we can extend the same property to the one parameter family of the different phase, which is a result of theorem B described the previous slide. Hence, the theorem A prime is essential of this study. We will now try to explain the idea of the proof as simple as possible. Okay, first, from the definition of F, call them this one. The first and third, also first and third, and first and third coordinate of this formula do not depend on Y. On the other hand, the second coordinate only depend on Y. Then the dynamics on the XZ plane and the dynamics on the Y axis are independent each other. Then, therefore, we can separate these dynamics into two maps denoted phi and psi, defined as follows. If the value of the right-hand side of the former equation does not depend on Y, we denote projected dynamics to the XZ plane by phi n. On the other hand, if the value of the right-hand side of the latter one does not depend on the X and Z, we denote the projected dynamics on the y-axis vertical direction by psi. This may seem like a rather specific situation, but without this situation, the proof is more complicated than it needs to be. So, to construct a wandering domain, which has a historic behavior or Dirac physical measure, we have to take 3 steps. The first step in proposition 4.3 in our preprint, we show that for any integer k and any sequence of code 0 or 1 for which the length is equal to the k to the power of 2, we detect the unstable bridge BUK. This is a projection of the blender to the strong unstable direction, and ghost CS bridge JCS of the next generation, which is the image of the unstable bridge by the projected dynamics. Note that CS direction, we do not have a control set, which is a projection of the blender horseshoe, but we have the invariant set controlled by the iterated function system on the blender. And we have the natural number n hat k and real number tk plus 1 such that the projected dynamics phi to the power of n hat k image of the middle point of the unstable bridge is located to the A2 inverse tk shifted from the middle point of the JCS of the next generation. Moreover, the norm of this shift can be taken arbitrarily small if k is so large. So note that ghost CS bridge is mapped to the next generation of the unstable bridge. Thus, we can do the same procedure in the next generation and more and more. This is a key mechanism of our paper using the unstable bridge and the CS direction controlled by iterated function system of the blender. The important thing is that we can use the distinguished property of the blender horseshoe to move the middle point of the unstable bridge to the middle point of the next generation. In the next step, using the previous proposition, any small neighborhood of F, we obtain shear diffeomorphism G satisfy following condition. In the complement of the yellow subcube around x equal to 1/2, this G is equal to F always. It doesn't change. But if a point belongs to the small rectangle for which the projected image to the strong direction and center stable direction are equal to some strong stable bridge of K generation and the CS ghost bridge K plus 1 generation, given the previous proportion for previous proportion respectively. It is mapped to by G2, the point just shifted along the unstable direction by tk plus 1, which is also given the proportion, previous proportion. To obtain such a G, in fact, we have to add perturbation in infinitely many countable places belonging to this yellow cube. For sufficiently large K, the norm of sum of all such a perturbation is arbitrarily close to the 0. Thus, we can get a G arbitrarily close to the arbitrary shear close to the F. But we have to, we must be careful here about the differentiability of the G in the method of our proof, also in the paper of Soma and myself, 2011. It is provable at any finite value of R, but R does not go to infinity. So our proof is not to apply to the C infinity topology. In the final step, we obtain a wandering domain using the previous proposition. In fact, for any large K, let us take a small cube WK in the yellow region as follows. Here the X hat is the middle point of some unstable bridge given in the previous proposition, and also bk and zk asterisk are constant defined by like that. This constant given in the previous proposition. Moreover, the yk is just a forward image of the strong stable biggest gap by projected dynamics along the strong stable direction. By using this cube, we have the following important theorem. There is an integer k1 such that for every integer k, at least k1, the interior of the wk, now denoted by dk, is a contracting wandering domain for d. We now get a different prism G arbitrary C1 close to the original map of F, which has contracting wandering domain. Next, we have to control the wandering domain so that it has a historic behavior or has a Dirac physical measure associated with some field point. We know that the wandering domain obtained this theorem with, which depend on the k, because in fact, the projected image to the local unstable manifold of the wandering domain is contained in the unstable bridge of k generation, or for which itinerary vk contain the sequence of elements which are chosen 0 or 1 freely and chosen and whose length is equal to the square of k. Using this arbitrariness of itinerary, we can control the dynamics of the wandering domain. In practice, to obtain the historical dynamics, we first consider the increasing sequence ks of integers satisfy following condition. Note that this condition provides us the situation that new error from the ks to until ks plus 1 to be so dominant as to ignore the old error from the k1 to ks minus 1. And under this error condition, we moreover set free part of the itinerary to oscillate alternately between even and odd error as follows. This implies that the next result, there is an integer k1 such that for above sequence of v, which is itinerary of the wandering domain, the different prism G restrict to the contractive wandering domain dk, depending on the sequence of v, has historic wandering domain, historic behavior. We now have a first half of the theorem A prime. Finally, let us explain how to show the second half of the theorem A prime, that is how to control G to have a Dirac physical measure associated with wandering domain. This is much easier than that of in the case of historicity. In fact, first of all, there is no need to consider error condition. In addition, the code condition is much simpler than that of historicity. In order to ensure the support of Dirac physical measure becomes a subtle fixed point P of blender, we just take a free part of the itinerary sequence of V to be O0. This implies that next result, there exists an integer k2 such that for above the sequence, which is depending on k2, G depending on this V has a non-trivial Dirac physical measure supported at the continuation of shallow fixed point PG and associated with contracting wandering domain. We now have to the second half of the theorem apply. Please see the following preprint for more detailed proof and explanation. Almost time. Oh, it is a little earlier to finish, but this is all for my presentation today. Thank you so much for your attention. Muito obrigado. That's all. Could you please question slowly or write it in chat on Zoom, because my English ability is not so high. So then, okay, thank you very much.
Thank you. Is any question?
I have a question or maybe a comment. You have this series of results that you have a type of tangency, higher dimension, and then you have this renormalization scheme that leads to this central unstable like families that has this blender-horseshoes without tangency. Do you think that it's possible to get a scheme of renormalization leading to this simultaneous, to this new type of horseshoes? Because at the end you have a iterated function system where one part is given by a central unstable like family, and well, you need another branch. But do you think about this?
Yeah, it's a good point, but we use a special blender which is asymmetric. So then by using the renormalization, it is difficult to find such a special situation.
Okay.
But yeah, it's somewhat different. Difficult.
Okay. You're right. Well, thank you.
Other questions?
The wandering domain, because you built a sequence of maps converging to your initial map. So is the wandering domain smaller and smaller, or is that a fixed wandering domain?
Yeah. It's wandering. So then.
No, yes. Is it shrinking smaller and smaller, or it is the same domain for every map?
Yes. It belongs to the gap of the blender.
This is fixed for every map, or you have that the size of that domain shrinks?
Yes. I think my wandering domain belongs to the gap of the blender. Yes. It becomes to the shrink. The diameter close to the 0, but it's wandering in the gap of the blender. Okay.
Okay. Thank you.
Okay, let's thank our speaker once again. We have we have a few minutes left. Christian.